Okay, let us start. So last time we started talking about interacting series, and here is the simplest interacting series with the Lagrangian density of the form okay, so this is just the simplest one, and we will use this as our example to illustrate how you treat interacting series. Okay, how you treat the particles with interactions. Once you understand how to do one series, essentially you know how to do all of them. And we also said that a key quantity when talking about interactions, a key observable is called S matrix. So S matrix is defined as the following. So S beta alpha equal to beta u plus infinity minus infinity alpha. So you start with some alpha initial state, which are widely separated, which you can treat as collections of free particles. And then say as t equal to minus infinity, they are very widely separated. But then as time evolves, they will come together, they scatter, then they will separate into far future. And so that's our final state, beta. And so S alpha beta is the transition amplitude between the two. Okay, so this is the written in terms of the Schrodinger picture. You can also written in terms of the Heisenberg picture, which is normally written in this form. Okay. So it's often convenient to write this S alpha beta separated into identity part, delta beta alpha, and then plus IT beta alpha. So this will capture the effect of the interactions. Okay, we'll capture the effect of interactions. And since the such a series, we always consider series which are both spatial and time translation invariant. So you have energy momentum conservation. And so IT beta alpha will always contain a piece proportional. We also put I here, proportional to the moment. Give you the momentum conservation. Okay. So P alpha and P alpha is the total initial momentum. So here is full momentum. Okay, so I suppress the indices, and the P beta is the total final momentum. So this part is purely kinematic. So the M alpha beta is the physical part. Okay, so this is normally called the scattering amplitude. Okay. So our goal is to be able to calculate the scattering amplitude. Okay, so this is something. Some version of the scattering amplitude can be measured in the experiments. So theoretically, we want to be able to calculate this quantity so that we are able to compare with the experiments. Okay. So we also mentioned, I will not repeat here, we also mentioned that this S alpha beta, S beta alpha also have various properties, which you should go back to your notes of last class to review them. So one of the key points is that there is this LSZ theorem, which says that which I just mentioned, that M alpha beta can be obtained from a correlation function like this. Say, for example, for that theory, okay. So the n would correspond to the total number of particles of the initial plus fellow states. Okay. Say, suppose you have 2 to 2 scattering, and then n would be equal to 4. Say, if you start from 2 particles, you scatter into 3 particles, then n will be 5. Okay, this is total number. Yeah. So later we will discuss in more detail how you obtain M alpha beta from here. But here, at the moment, it's enough for us to know that the scattering amplitude can be extracted from this quantity. Okay. Oh, sorry. I should. So here should be time ordered. Okay. And so let me just explain the notation here. So the omega is the vacuum of your interacting theory, and then the T is time ordering. Okay, so it means that the whoever with the larger time will appear earlier. Okay. Whoever with a larger time will appear earlier. And so any questions on this? So our goal would be to tell you how to calculate this quantity. Okay. So once you know how to calculate this quantity, then we will be able to calculate the scattering amplitude, and then you will be able to compare with experiments. Okay. And good. So in principle, we already know how to calculate this quantity from what you learn in 806. So for people who have taken 806 here, you learn, yeah, so we mentioned last time this theory cannot be solved exactly. And the only way we can treat this theory is take lambda small and then treat this as a perturbation. Treat this as a small perturbation, and then expand all your physical quantities in power series of lambda. Okay, so this procedure is called the perturbation theory, and in your quantum mechanics class, you should have already learned how to do perturbation theory. For example, in 806, that's a big part of the 806 class. Anyway, so just with 806, in principle, you already know how to do this. Let me just outline the procedure. Okay. A computation. So that is of correlation function. So that's just it's called a time ordered correlation function. So what I will call this is a naive perturbation theory. Okay, so this is the perturbation theory you would do after you learn 806. Okay, after you learn 806, and then you will be able to do this perturbation theory. And but we will, yeah, but we will do something more clever. Okay, we will do something more clever. But let me just remind you, equipped with your previous quantum mechanical knowledge, how would you treat this problem? Okay. So now let's consider that again that theory as an example. So equation motion give you partial square minus m square phi equal to say lambda divided by 6 phi cube. Okay. And so we can treat this, we can solve this equation, even though we cannot solve this equation exactly, we can solve it perturbatively in lambda. Okay, So the way we do is the following. We write phi equal to phi 0 and the lambda phi 1 plus lambda square phi 2, etc. Okay, so lambda is a small number. You imagine you expand phi in power series of lambda. And then you just plug in this power series into this equation. And then you equate two sides with the same power of lambda. Okay, with the same power of lambda. So at the 0th order, you just get our previous equation, phi 0 equal to 0. So phi 0 is just like our previous free field equation, okay, the previous one. And then at first order, then you see phi 1, and now you have 1 over 6, phi 0 to the cube, okay, and then etc. Okay. So this equation we know how to solve. And once you know how to solve this equation, you find a solution for phi 0, then you plug it in this equation. And now this just becomes a linear equation. Now you can solve phi 1. And similarly, you can solve phi 2, etc. Okay, so order by order, you can solve all of them. And all of them become linear equations. Okay, so phi 1, all higher orders can be solved in terms of phi 0. Okay, so once you find the phi 0, and then phi 0 become can be solved in terms of phi 0. Okay. So classically, this gives you a solution, and as we said, quantum mechanically, we just treat this, treat all this as operator equations, and then essentially you can just solve the phi perturbatively as the operator equation, as a quantum operator, okay, and then you solve this quantum operator equation, okay, perturbatively. So similarly. So similarly, we can solve this omega, okay, using perturbation theory. So first we expanded this omega in power theory. So this is the vacuum of your interacting theory, and we expanded in terms of perturbative series. Okay, so the 0th order, you just get the free theory vacuum, okay, and then you will have corrections due to the corrections from the lambda here, okay, due to you have interactions, and yeah, because of your Hamiltonian change, because of the lambda, your Hamiltonian change, and so your ground state will also change, and so you can now you can use your 806 to work out those. Higher order corrections. Okay. Yeah. So now when you worked out the phi, when you worked out the omega, okay, now you can work out this object. So let me just call this Gn. So the Gn then can be reduced to a calculation in free theory, okay? Okay, and using perturbation theory, because everything can be expressed in terms of phi 0, and here again you expand in terms of phi 0, and the corrections can be obtained by, say, acting the phi 0 acting on the a vacuum state, etc. So in the end, if you do this procedure, and then you should be able to calculate this Gn. Okay. Conceptually, it's not very difficult to calculate. Okay. And but this procedure is actually very complicated. So yeah, I don't urge you to try it yourself, but I think you should try, just to get the sense that this procedure is actually not very easy to do. Okay, so that's why in quantum field theory you actually need to develop a more sophisticated technique to treat this, because yeah, that's what people did in the early days. In the early days, before systematic perturbation technique for quantum field theory was developed, that's how people did in the past. Okay, and it was not easy, but people did it. Did it. Okay, so if you want to calculate the first order, it's actually doable, but doing to higher orders become increasingly complicated, and yeah, so become quickly become very complicated to go to higher orders. Okay, at higher orders. So eventually people develop something more clever. Okay, so eventually people develop something more clever. So there are two approaches. There are two more sophisticated approaches, which are in the end are equivalent. Okay, in the end are equivalent, and but the derivation is different. Okay, so the first is to use so-called interaction picture. Okay, is to use so-called interaction picture. So what you do is the following. So you separate your Hamiltonian, total Hamiltonian in terms of free series Hamiltonian and the interacting part. Okay, so the free series Hamiltonian just come from, say, the free, if I write this as L0 minus that plus Li. So this term is Li. Okay, so this part is L0. And so similarly, you can write your Hamiltonian also separate into the free series Hamiltonian and the interacting part. Okay, and then the interacting picture is that you introduce the state in the interacting picture, and you introduce the operator in the interacting picture. Okay, so the state in the interacting picture are related by the standard state in the Schrodinger picture okay, so let me just put the S here. So this denotes the states in the Schrodinger picture through this factor of H0, essentially H0t. Okay, and the operators in the interacting picture are related to the operator in the Schrodinger picture also through this factor of exponential H0. Okay. So already in your quantum mechanics, you may have discussed the interaction picture. Have you seen interaction picture before? Yeah, yes. So remember this evolves with the full Hamiltonian. In the Schrodinger picture, this evolves with the full Hamiltonian. And so here your interaction picture related this by evolution operator, conjugate of the evolution operator for the free Hamiltonian. So this psi I still evolve in a complicated way. Okay, so in the interacting picture, the states still evolve in a complicated way. But the operator evolve very simply because because in the Schrodinger picture, the operator don't evolve, and here the evolution just controlled by the free Hamiltonian. So in the interacting picture, the states still evolve complicatedly, but the operator evolves in the simple way. Anyway, so with some manipulation, you can by introducing this interacting picture, you can design a more clever way to do this the perturbation theory. Okay, and so I will not go through it here. You should read the Paskin the book Paskin and Schroeder, section 4.2, and there they give a detailed discussion how you do perturbation theory using this interacting picture. Okay. So the second approach is to use the path integral. Okay, just do the path integral. So path integrals, in my own opinion, have a lot of advantage over this interaction picture. So when you do interaction picture, you get the feeling somehow you're doing some very clever tricks, okay? And you don't know why you want to do those tricks. And somehow you get some nice formulas, but somehow you feel you're doing a little bit, you're doing some kind of magic. But the path integral treatment is automatic in the sense it's straightforward. You don't have to think, okay? And it just follows from the path integral. And it's much easier to generalize, and it's physically intuitive, and so that's why we will describe this approach. And because it's more physically intuitive. Sometimes when you do too much fancy mathematics, you feel you obscure the physical picture, and so this interacting picture give you a little bit that kind of feeling. So we will. But it's important for you to know it. We don't have time to cover both, and so we choose just to do this in class. Yes, you have a question?
The interaction picture. Why do both state and the operator go according to H naught? Shouldn't the state go according to the interaction?
Yeah, just by design.
Oh, okay.
I just define them this way.
Oh, okay.
I just define them this way. It turns out the quantity defined this way is actually convenient for doing perturbation theory.
Yeah.
Right. Yeah, so that's why I say there's a little bit of magic here. And you have to introduce this kind of unintuitive quantities, which turned out actually to be quite simple when you do perturbation theory. Yeah. Okay, good. Any questions on this? Okay, now let's just go plug into the path integral. Okay, now let's just plug into path integral. So path integral is an alternative way to formulate quantum mechanics. It's equivalent, say, to the Schrodinger equation or Heisenberg equation. It's equivalent to your standard way of thinking about quantum mechanics. So path integral give you a better conceptual way. For non-relativistic quantum mechanics, path integral, most of the time, they give you a better conceptual way to think about quantum mechanics. But in terms of calculations, it often does not offer any advantage. So that's why the textbooks for undergraduate quantum mechanics, they don't just do path integral, okay? Because to calculations, it's still much easier to solve Schrodinger equation. But conceptually, it's give you a better picture. And for quantum field theory, actually become much more useful. Okay, become much more useful. Is there any questions on this? Okay, good. Okay. Okay, so first we are going just to do the review the story for the non-relativistic quantum mechanics. And once we understand this, and the immediate generation to field theory is immediate. Okay, a generation to field theory is immediate. So we will just use an example of just one particle, just a particle in one dimension. Okay, just with the most familiar one. Okay, so use this as an example. Once we understand this example, then you essentially understand everything. Okay. Good. So now the key point about the path integral is that normally previous in quantum mechanics, you start with the Schrodinger equation, but the path integral start with a different object. Okay, start with a different object. So the object which the path integral is most convenient to treat is the propagator we discussed before. So this is the object which is we defined to be the, in the Heisenberg picture, to be this object. So this is the transition amplitude if you have a particle, if you have eigenstate with x prime at t prime, and go into a position eigenstate at the location x at time t. Okay. So we mentioned before, if you load this object, and essentially it's equivalent, you have solved the Schrodinger equation. Because from the wave equation at t prime, then by integrated with this, convoluted with this object, then you can get the wave function at time t. Okay. And so this can also be written in terms of Schrodinger picture as this. Okay, you just it's the start with the position eigenstate at x prime, then you evolve for t minus t prime, and then you ask the overlap with the x. Okay. Any questions on this? So let me call this object K. This is K, x, t, x prime, t prime. Okay? If you know the wave function, so the wave function at tx can be written as a wave function at dx prime, k, tx, t prime, x prime. Oh yeah, I think I changed the order. So just to be consistent with the order I wrote there. T prime psi T prime X prime. Okay, so if you know the wave function at T prime, and then by integrate this, you know the wave function there. Okay, so this is so knowing this object, then it's equivalent to knowing to solve the system. So now we will describe a way to compute this object. Okay, we will find a way to describe a way to compute this object. So do you have any questions on this? Good. Okay, so we will do this by using a trick. So we have, so imagine this is your time axis. So we start with t prime, and then we add n at t. So this is time axis, n at t, okay? So what we will do is we divide this segment, divide this interval by infinite number of segments. Okay? And each segment is infinitesimal, of course. So we have, say, label this point by 0, 1, 2, etc. Okay? So t0 would be just t prime. Okay, and the last point would be n, and the tm would be t. Okay, so we divided by this by n intervals. Okay, so the width of the interval is delta t equal to t minus t prime divided by n. Okay, so here is delta t. Okay, and we take n go to infinity, and then this interval go to 0. Okay. So the reason for considering this is now we can rewrite expansion minus iht prime, okay, in terms of many ih delta t and then n times, okay? Okay, essentially I have n times. Okay? So now what I'm going to do, so then we have this x. say exponential minus IHT minus H delta t. So now let's write this n times separately. X prime, okay? So now let's insert. So the mathematical trick we are going to use, insert at each, between each such factor, a complete set of states. Okay, a complete set of position eigenstates. So we insert, yeah, so insert at ti. Yeah, because the yeah, so here is t0, then going to here will be t1, etc. Okay, so at ti, so you insert the complete set of eigenstates. So you just insert 1, okay? Position eigenstate. So now this object K then can be written as then dx1 dxn minus 1. So at each here you, okay, and then you have say x exponential minus h delta t xn minus 1. Okay, and then all the way here into x1 exponential minus iht h delta t x prime. Okay. So the purpose for doing so is that now we can calculate each of such things explicitly. Okay. Now we will see. Okay. So now let's consider just one of such factor. So factor here have the form xi plus 1 exponential minus I h delta t xi. Okay, so any factor here have the form for some value of I. Okay. So I start from 0 to all the way to n minus 1. Okay. So now let's compute the computing this quantity. And now this quantity is actually computable, even though this object is very hard to compute. Even though this object is very hard to compute. Okay, this object is very hard to compute because you have the potential there, etc. We don't know. In general, we don't know how to compute this exponential. But now the trick is that once you separate them into infinitesimal steps, and then we can actually calculate the infinitesimal step. And once you can calculate infinitesimal step, you just add them together, then become the whole thing. Okay? So that's the basic idea. So to do this, contain two elements. So the first element is to recognize. So now remember h here is the operator. So let me just to emphasize here. Okay, now let me put a hat here just to emphasize here is operator. And so if you write this explicitly, so this is I or minus I delta t, and then you have p squared divided by 2m. Let me just also put the to emphasize the operators and v hat. Okay. So now, because of the delta t is small, goes to 0, then to leading order in delta t, so this is the first element. Okay, the first element is point. Then to leading order in delta t, we can actually just separate the exponential. We can say this is approximate equal to exponential I delta t p hat square by 2m, and the exponential I delta t v hat x. And the only corrections are order delta t squared. Okay. So this you can easily see from the Campbell or Baker. Yeah. Anyway, BCH formula. so from the BCH formula, let me write it here. Exponential a plus b is equal to exponential b, and then exponential minus half a commutator b, then plus with more commutators. Okay. And now each a and b are proportional to delta t. So here is proportional to delta t, here proportional to delta t, and here involve at least the product of a and b. So here is all higher order in delta t squared. So this is one of the key reasons we want to do this. We want to separate into individual steps, okay? Because we can factorize them. Because in general, we cannot factorize this guy. This guy is very complicated because p and x don't commute. In general, we cannot factorize them. It's very complicated. For finite t here, we cannot factorize them. But for delta t, we can factorize them. We get this structure. Okay? So once you have this structure, and then this thing becomes easy to compute. Okay, so now you can, the second thing you can show So the second thing you can show, now you can show that xi plus 1. So now you plug in this factorized form into this expression, okay? And now you can compute this. So you have minus I delta t, p hat squared divided by 2m, minus I delta t, x hat, and xi. So those are just eigenvalues, so there's no hat, but here there's hat, they are operators. Okay. So here you can now compute this object. So this becomes elementary exercise in quantum mechanics. Okay, so I will not, there's like 2-line calculation here, I will leave it to your homework. So you can calculate this object. So let me just write down the result, okay? So this becomes the following object, m divided by 2 pi I delta t exponential. So you can evaluate this explicitly. 1/2 im xi plus 1 minus xi delta t squared delta t minus I delta t. Dx. Okay, so you just get this. Okay, so this is the answer. So this is the second element. That now this is readily computable using the standard technique. Okay, so this is the, I will remember to put it in your homework. Okay. So now, we have to use a little bit imagination. So now we have to imagine, use a little bit imagination. Yeah, I should have drawn this line longer or bigger. Yeah, let me just draw this line a little bit bigger. Sorry, I drew this line too short. So let me just draw this longer. So here is t prime. Here is t. Here you have different locations. Okay, so I also draw the delta t to be big. So at each ti, you have xi, we insert the xi, okay? So this is ti, we insert the xi. So x1, so at t1, we insert the x1, etc. Okay? So now you imagine for each value of x, because in the end we need to integrate of all possible x. Okay. So for each particular value of x1, x2, x3, xn, okay, we can view it as a function of t evaluated at that point. Okay, so now let's imagine. Now let's consider you have a function xt, so that when you evaluate it at ti, the value is xi plus xi. Okay. So if you think this way, and now the thing in the exponential become a very familiar object. So what is this object? Yes?
The Lagrangian.
Exactly, just become the Lagrangian. Because this is just like the time derivative. So this is just like x dot square. And this is just like v times delta t, okay? So this is just like, so this is equal to, okay, so go from here to here. Now this is just equal to, with the same prefactor, just become exponential I delta t times your Lagrangian density. Yeah, just a Lagrangian here, just a Lagrangian x dot evaluated at xti. Okay? So you have the Lagrangian. So remember the Lagrangian is just 1/2 mx dot square minus bx. Okay? So if you take out this delta t factor and this I factor, and then this just becomes 1/2 mx dot square, and this just becomes v, all evaluated at xi, and xi is the value at ti, so all evaluated at ti. Okay? So now you recognize, you just get your Lagrangian there. Okay, just get your Lagrangian there. So now we can write down the full t, full k. So now the full k become limits n go to infinity, okay, because we take delta t go to 0, okay. So we need to take the n go to infinity. So m 2 pi I delta t to the power n divided by 2. So each one give you square root, and then you have dx1, dxn minus 1. But now the integrand become I delta t. Now you just sum over I from 0 to n minus 1 L, your Lagrangian x prime divided at ti. Okay? So you just, because now the product in the exponential just become the sum. Okay? So now you recognize this essentially is the discrete version of the integral of L with dt. Okay, it's just the over time. Okay, so now we can write. So the exponential we can essentially. So let me keep this integral here. So the exponential part we can write it as exponential times I from t prime to t, say dt double prime L x dot. Okay, so this just become that. The integrand just become like that. But we still have this whole bunch of complicated stuff. Okay, take n go to infinity, this thing. So normally when you have something complicated, again, there's an unfailing trick in physics to do it. What is that trick? Do you know?
Give it a name.
Exactly, we just rename it into something simple. So we just call the whole thing dxt. Okay, this is just supposed to represent these limits. Okay. And so with the condition that xt prime equal to x prime and xt equal to t, or xt equal to x. And the meaning of this dxt, okay, the meaning of dxt, if you think about it, as I mentioned, each particular choice of x1 and to xn minus 1, you can think of some function of x evaluated at ti. So now you integrate over all possible such values, and then just corresponding to you integrate over all possible such functions. Okay, you integrate all possible such functions. So this just corresponding to integrate all functions xt satisfying. So mathematically, this means satisfying that the xt prime equal to x prime and xt equal to x. Okay, so because we always fix the two endpoints. Okay, you only integrate in the middle. Okay, you only integrate the middle. So now this has a very simple physical interpretation. So now this has a very simple physical interpretation. So integrate over all possible functions x between t and t prime with endpoint fixed. Physically, this just means, suppose we call this is the, say this is the t, this is the x-axis. Okay, so suppose that the t prime is here. So here is the, say, x prime at t prime, and so this is the xt. So this is the x prime t prime, and this point is x and t. So you integrate all possible functions between them, just corresponding to, you just imagine you integrate over all paths between them. Okay? You integrate over all possible paths between them. Okay? So this is the same as integrate of all paths. Okay, between them. Okay? And then it's weighted. Okay, and each path is weighted, the integrand is weighted by exponential is. Okay, and s is just your action. Okay, so this is the from, again, it's from the t prime to t. Okay. Yeah, let me just write down. Yeah. So by this factor, okay. So the integration of the Lagrangian is just your action, okay. And then you find that now you can write this transition, propagate this transition amplitude in terms of such expression corresponding to integrate all possible paths, sum over all possible paths, and with the weight by the action, exponential I action. Okay. So this started as a technical trick, okay, as a technical trick, because computing this thing is complicated. And then we can make mathematical progress by dividing them into small intervals. But once you do that, but now we obtain a different way, but now we actually obtain something conceptually new, okay? You just say the quantum mechanics. So classically, remember, classically, there's a fixed path from xt prime to t, just follow the equation of motion. But now we say quantum mechanically, we just sum over all possible paths. So that's the quantum uncertainty compared with the classical mechanics, okay? So starting with that mathematical trick, but now we actually obtain something conceptually brand new. Yeah, just quantum mechanically, the difference from classical mechanics, just now we just sum over all possible paths, which is physically very intuitive, because quantum mechanically you can just go anywhere. Okay, just uncertainty principle. Okay. Good, any questions on this? Yes?
Are there constraints on what path we integrate over and possible? Does it have to be differentiable?
Yeah, this is a good question. So to make sense rigorously, this quantity is actually, yeah, to make rigorous, this quantity is not easy to do. So we will not go into there. That needs to go into lots of mathematics. We don't, yeah. So normally we don't need to worry about the precise mathematics, how to define that path. Mostly we think this from the conceptual picture. And also when we do technical manipulations, as we will see, often you don't need to know the details, how you define this measure precisely. Yeah. Yes?
Similar question. There's no coming back in time. That's right.
In principle, you can. Yeah, there's no coming back in time. Just from here to there. Yeah, there's no coming back in time. But the path can wind around as you want. Yeah. But the time you cannot come back. Yeah. Other questions? Okay, good. So there's also another form of this path integral. So I will not do it here. It's a slight variance of this. Let me just write it down. Again, I can put it in your homework. So there's also a Hamiltonian form, which is much less used, but sometimes it's also useful. It's a Hamiltonian form. So you can also write the k, same object as the following, as x. Again, the same boundary condition, xt prime equal to x prime and xt. So you integrate over all possible paths as here, but you also integrate over all possible momentum within this time range. And then the integrand becomes the Hamiltonian. Okay, you write it in terms of the Hamiltonian. So t prime t dt double prime, then px dot minus h. Okay, so h is your Hamiltonian, and p now is just some function, some arbitrary function. And so for any choice of x and t, p, you can evaluate this quantity. Okay, and then you sum all of them together. Okay, and so this alternative form, which can be easily, again, a couple of lines, which you can show to be equivalent to this form. Okay, to be in that form. And to show this is related to the second step here. So intermediate step of doing this one will lead to this one. Okay, will lead to this one. Good. Any questions? Okay. So now let me just talk about the example. So how you can use this method to calculate, say, some systems, okay, simple systems. And so as I said, this method is not very efficient for non-relativistic quantum mechanics. And even though offer a different conceptual picture, and you can see from those examples, okay. So now let's consider a simple case. So we just consider free particle. So there's no V, okay? So just consider free particle. So here S just 1/2 mx dot square. Okay? Yeah, let me just use Q since my notes use Q, doesn't matter. So let's try to compute in this theory the amplitude, let's call ZT. Say at time 0, you are at Q equal to 0. And then at time t, and then again you're at Q equal to 0. Okay, so you just come back to the same point. Okay, come back to the same point. So corresponding to this situation, if you call this direction to be t, and this direction to be q, so at some initial point you are here, and your final point at some t, the value of t, again you go back to the same point in q, and then we just sum of all paths here. Okay? Sum of all paths here, but free particle. So in order to compute this guy, now we have to work with this, because this is only a formal notation. Remember, this is a formal notation for this object. Okay, if you really want to compute this, so this is called the path integral. Okay, so this is called the path integral. So if you want to really calculate this path integral explicitly, and then you have to go back to this form. Okay, you have to go back to this form. So so the ZT is equal to, so in this case, limit n go to infinity. So yeah, let me just not copy. Anyway, you can write down. You just copy this down. Okay, just change this to just to save time, and change this xi to q. Okay, change this q, and now the integrand you only have 1/2 mq squared. There's no v term. Okay, a v term. You can just plug that in into here. So now in principle you can calculate that integral, and I will leave it to your exercise to do. Okay, in your homework, and you find that it will recover the standard answer. So at the end of the day, when you do this integral, this many integral, then you find that this gives you actually I didn't write down the final answer, which let me see. Yeah, so you find the final answer is a very simple one, just 2 pi it square root. Okay. So you can do this infinite number of integrals, and then you find it give that answer. Of course, you can calculate that thing easily by solving the Schrodinger equation using your standard method. But this is a good exercise to do. Okay. So this is one method to calculate it, but this method is not very efficient. Okay, because each time if we have to go through this limit, and it will be very annoying. Okay, it will be very annoying. So so now there's a more abstract method. Now there's a more abstract method, but much less mathematical rigorous. Okay, you can make it mathematical rigorous, but I'm not going to make it mathematical rigorous. And but it's when you get used to it, it's much easier to manipulate. Okay, so now I'm going to talk about second method to calculate this. So this is the first method. You just do honest integral. Okay, do the honest integral. So the second method call this 1, so the first method. In the second method, so in the second method, let's first look at this. Oh, yeah, sorry, this should be integrated over dt. So this is like MQ square is a Lagrangian. Here we're talking about the action. So here we look at the action which appear in the path integral in that formal form. Then you have S is equal to 1/2 m. Then you have dt from t equal to 0 to capital T. Okay, from t equal to 0 to capital T. And then we have 1/2 mq dot square. Okay? So we have that. So now I'm going to slightly rewrite this expression. So I'm going to write as following. M from 0 to t dt, I will do integration by parts. Oh, sorry. So I'm already out. Then I have q minus partial t square q. Okay? So integration by parts, so the derivative only act on one of the q. So I get the minus sign. And the boundary term is all 0 because the q at the initial and the final value are 0. Yeah, so you can check yourself. Okay? So now I'm going to write this expression a little bit further. I'm going to introduce 2t, t and t prime. I write it as q. Yeah, let me just write it as 1/2. Let me just write it as 1/2 q t, and I write here as minus m delta t minus t prime partial t prime square q t prime. Okay? So these two are the same. So I introduce additional t prime, but also I introduce a delta function. So when you evaluate that delta function with t prime integral, you just get back to that the expression above. Okay? So now I'm going to call this thing to be k. Yeah, actually, sorry, I want to put this minus sign out just for convenience. Okay, just so let me just call this in k. Okay, so what I get is the minus. Yeah, it doesn't matter actually. So sorry. Let me put it here. Yeah, it doesn't matter. So here we can just write 1/2 dt prime qt k t prime qt prime. Okay?
Question?
Yeah.
What's the integral over dt prime?
Yeah, integral of dt prime, you can just evaluate using this delta function, and then just go away. And then just here, just all become t, then you just reduce to that.
So is it like an all-time integral?
Yeah. Oh, no. It's the same from 0 to t.
Okay, they're both.
Yeah, the same range. So now I just call this thing to be k. Okay? So now, I think we have done this before. And now I want you to view this t in Q as an index. Okay, imagine this is just a continuous index. And then Q is just like a vector. Qt prime is like a vector. Qt is like a vector, and this is the same vector. And now this is just a matrix between the two vectors. Okay? So now we can view Qt as a vector with t as index Okay? And then the K is the matrix. It's a matrix in the space of Qt. Okay? So if you view, so when I write this form, then this integral dqt, so then we have this dt equal to dqt. So for simplicity, let me just suppress the initial and the final just for simplicity. And then you just have I, then 1/2 I dt prime. Also, let me just suppress the, then you have q dot k dot q. Okay, let me just use this simplified notation. Okay, you should view just this is the same as that guy. Okay, yes?
Is it like ad hoc that you left the first q as a function of t and not made it a function of t prime instead?
It doesn't matter. You can do that way too. Yeah, won't change. Okay? So now you compare this form with, so now this is look like a Gaussian integral. Okay? Now this is look like a Gaussian integral. So now let's recall your Gaussian integral, which we're familiar with. When you have dx exponential minus a divided by 2x squared, then that gives you 2 pi divided by a. Okay? And now if you have, so this is a one-dimensional integral, but you can also have an n-dimensional integral. Okay, so here the indices are summed. So this is equal to 2 pi to the power m divided by 2 square root delta A of this matrix A. Okay? So now this integral is just the generalization of this integral, except the index become continuous. Okay? And here the k have two indices. It's just like mn. So here is like qm and qn, and this is just like mn. Okay. So this is just like an ordinary. This is just like a Gaussian integral, but in the space of infinite dimensional vectors. Okay. Yeah. Of course, not just infinite. It's uncountable infinite dimension. Okay, because it's a continuous index. Okay. So now, with this understanding, with this realization, we can just directly write down the answer. We say, then the ZT, okay, must be just given by some constant divided by delta K. Determinant K. Okay? Yeah, you just generalize this formula. You generalize this formula. So just now K is in the determinant in the more complicated space, in the space of functions. Okay? So the only unfortunate thing is that both C and the delta K is actually are divergent. so C is some constant. And the delta K is the determinant of K in the space of functions. Okay, so this is like the K is the matrix. It's a matrix defined in the space of QTs. Okay, QT is the space of functions. Okay. So so this constant can be divergent, but this doesn't matter, as we will later see. Such a constant never matter, don't matter very much for your physics. Okay. And yeah, as I warned you before, in quantum field theory, we'll see divergences everywhere. So the key is to recognize which divergences are important, which divergences are not important. Okay, so unimportant divergences, we just forget them. Okay. Yeah, so we will later see that such a C will always cancel when you consider physical quantities, and so will never matter. Okay, will never matter. But still, we need to talk about how to think about the determinant. Okay, what do you mean by determinant here? So we do it in the same way as you would do in the matrix space. So if you have a finite dimensional matrix, there's a way to calculate the determinant, yeah, the standard way, which you land in, yeah, say A1, A11, A22, etc. That's a complicated formula, okay? But that way does not generalize to such K which with a continuous indices. So we must find a way to generalize the determinant here in a way which can apply to such a K which is defined in the space of functions. So there's another way we can calculate the determinant of A without using the standard formula. So you do it as follows. Remember, the determinant of A is also the product of all the eigenvalues of A. So you can just find the eigenvalues, all the eigenvalues of A, you take the product of them. And then that is the determinant of A. So this way to define determinant actually generalize. It doesn't matter how many eigenvalues you have. So now we can just find all the eigenvalues of K. Okay, just find all the eigenvalues of K, and then we just take the product of them. That gives us the determinant. Okay, so this is the way which you can generalize. So how do we define the determinant eigenvalue? So when we define the eigenvalue of A, Mn, we find the eigenvector x, so satisfy this behavior. Okay, so the n is summed, and then give you us, right? So now the analog of the Mn here is T and T prime. So the analog here is from 0 to T, T prime, K, T prime, some function Fn. Yeah, so n here label different eigenvalues. Yes, so let me call it I, T prime equal to lambda I, Ft. Okay? So this would be the eigenvalue equation, because now the n index here just replaced by T prime, the sum over n just replaced by integral, and then the rest is the same. Okay? So you just find all the eigenvalues of K and Ft, and of course should satisfy the condition that the F0 equal to say Fi, yeah, Fi t should satisfy the boundary condition. This equal to 0, because that's the integral. That's the condition of a path integral. Okay, the path integral is set from 0 to 0. Okay. Yeah. Okay. And you just solve this eigenvalue problem. This is a well-defined mathematical problem, because K is just a differential operator. K is just some differential operator. And now this becomes a well-defined mathematical problem. We can find these eigenvalues. and then we just take the product. Okay, so this way we generalize that formula. So this is an exercise for you to do yourself. Okay, K is just a quadratic differential is just partial t squared. It's very easy. Okay, it's very easy. So you find FIT. Yeah, actually, I think I is also another very fortunate notation because the can be easily. Yeah, let me call it J. Okay, so pi J T, and then divide. Yeah. So you can just solve this equation easily yourself. Okay. So let me just write down the answer. So the eigenvalue are pi Jt divided by capital T, and with eigenvalues lambda j equal to m j squared pi squared divided by t squared, and the j equal to 1, 2, etc. Okay. So even though the k, both index of k are continuous, but the eigenvalues are discrete. Okay, are discrete infinite. The eigenvalue is discrete infinite. You just labeled by integer j. Okay, you can easily convince yourself. Yeah, just solve this equation. Okay, it's easy to solve. So now we can find the determinant of k. Okay, now we find determinant of k. So this is given by product of n equal to 1, j equal to 1 to infinity, m j squared pi squared divided by t squared. Okay. So you say, what is this beast? So we have all these infinite things, we have these things, we have all these constants multiplied infinite times, and then we have this j squared, okay? And so now I claim, okay, again, I will not have time to do it here. Okay, I will claim this guy, once you do proper things, and then that gives you that answer. Okay, when you do that C over delta T, that can give back to this answer. Okay, give back to that answer. Okay, so you will walk through that in your homework problem. Okay, or your homework problem. Okay, so this way, even though it looks hairy, but once you get used to it, it's much easier than doing those integrals and take the limits. Okay, it's much easier than doing this take a limit. And also we will later see, most of the time you actually don't need to calculate the determinant explicitly. Okay, later we will see most of the time you don't need to calculate determinant explicitly. You don't need to use those things, and just the path integral framework somehow provides a platform for you to do lots of things. Okay, you don't actually need to evaluate it. It actually provides a platform. That's the most important thing about the path integral. It's about often not about how you evaluate it. Okay. Good. So before we conclude, let me just make some further remark. Yeah. Because it's better we just make a couple of remarks here so that we don't forget next time. Yeah. So we have. Yeah. Give me like 2 minutes to make some remark. So one remark. So one remarks I already said is that this is a new formulation of quantum mechanics. Give you a new conceptual way to think about quantum mechanics. Okay, give you a new conceptual way to to think about quantum mechanics. And you can show that these two formulations are equivalent. Okay, so this is equivalent. You can show that this is equivalent to the Schrodinger approach. To the Schrodinger formulation by showing that the k you calculate it this way. Okay, using path integral, you find that this k. You can show that the k actually satisfies the Schrodinger equation. Satisfy the Schrodinger equation. So this will guarantee, I already erased that guarantee your wave function when you convolute to this k will also satisfy the Schrodinger equation. Okay, so you can show that this actually satisfies the Schrodinger equation. So you can show that the k actually satisfies the Schrodinger equation. Again, I will leave it to your homework. Okay, to your homework. Good. And the second point is just to highlight this contrast between the classical mechanics, which you have a fixed path determined by equation motion, and the quantum. Okay, you just sum over all possible paths weighted by your action. Okay, you just sum. Just a contrast, okay, just a contrast. And let's stop here. So the next time, then we are ready to go to field theory, okay? So with this, if you're familiar with this, get used to everything here, then going to field theory just immediately, you just change the rotation. Because as we said, the field theory just corresponding to quantum mechanics with infinite number of degrees of freedom. Once you understand 1 degree of freedom, then you can just generalize to infinite number of degrees of freedom just by changing notations. So this aspect will be the same. Okay, so we can immediately write down the path integral for quantum field theory next time. And then we can talk about the interactions.